So in thinking about putting electrons into these orbitals in a multi-electron configuration, we're now going to simply fill up the orbitals in the order of increasing energy. That is, first we're going to put as many electrons as we can into the lowest lying orbitals before moving up to the higher. And remembering the Pauli exclusion principle that none of our electrons can have the same quantum numbers, that means we can only have 2 electrons in any given orbital. So we'll put 2 in the 1s, and then we'll have to move up to higher in energy and put some in the 2s and then the 2p and so forth. To remember this filling order, there are a couple of tricks that you can use. One is you could write out some diagram here where you have the 1s and then the 1s and the 2p and the 3s and the 3p and 3d and so on, and then you can draw diagonal arrows and that will give you the order. 1s first, then 2s, then 2p, 3s, 3p, 4s, 3d, so on and so forth. Alternatively, you can use the periodic table. So here is the periodic table written in a traditional way where the groups are numbered 1a, 2a, 3a, so on. But you'll also see them numbered this way where we just move across 1, 2, 3, 4, 5 all the way up to 18. We can also take the periodic table and group it like this, which shows us the different blocks where the highest energy or valence electrons in those atoms come from different subshells. So this pink block, the valence electrons are s electrons. That is, those are electrons with L equal to 0. And the blue block is the p block. That's where the valence electrons now have L equal to 1. And then in the middle there, we have that big place we have to insert where all of a sudden we start to have L equals 2 available. So once we get up to n equals 3, we can slip those in. And then finally, at some point, we need L is equal to 3. That's the F block, and they sneak in at the bottom. So if we put these all on there, we can see that we're going to fill the 1s, and then the 2s, and then the 2p. So as we move left to right across a row and fill it up, and then we move back down and we start the next period. 1s for hydrogen, second 1s for helium, then we have to move back and start with the 2s's, fill up the 2s's, fill up the 2p's, then the 3s's, then the 3p's, then the 4s, then the 3d. It's important to remember because there are 3p orbitals, we can fit in 6 electrons in the p block. Because there are 5 d orbitals, we put 10 electrons in the d block, and again 7 f orbitals, we're putting 14 into the f block. So this order will almost always be the same, filling up from the lowest energy and going higher. 1s, 2s, 2p, 3s, 4p, so on. And you have to remember how many electrons we can fit in each. So there's 2 in the s, because there's 3 p's, you get 6, 5 d's, you get 10, and 7 f's, you get 14. Another important idea is Hund's rule, and Hund's rule tells us that we always fill degenerate orbitals with a single electron before pairing them. This is because it turns out that having that configuration provides a lower energy. This is an idea that we get from quantum mechanics about maximizing the multiplicity. But our drawings here don't really do justice to the quantum mechanics, but it's important that we realize how many electrons we have that are paired or unpaired, because that's an important property that a particular atom might have and really affects how it interacts with magnetic fields. So if we're filling the 2p's, if we have one, we can stick it wherever we want, but when we put the second one in, it's important that we put it in a different orbital. And traditionally, we just go left to right, although that doesn't have any particular meaning, and we usually give them the same direction, both up. But again, that doesn't have any particular meaning, it's just convention. We get to our third, and now again, we want to put it in its own orbital before we pair them up. So when we move to the fourth electron, now we have to start pairing, and then the fifth, and then the sixth. Hund's rule, always fill singly before pairing begins with degenerate orbitals, that is, the ones that have the same energy. Finally, let's see what happens as we just start filling up electrons. Now here we've drawn them just generically spaced apart. Again, this does not represent accurately what the energies are. There's a much bigger gap between 1s and 2s than there is between 2s and 2p, but for convenience on the screen, we just put them equally spaced. So if we have hydrogen, it has 1 electron, we put it in the 1s orbital, and we would say that configuration is 1s1. Helium, 2 electrons, put them in the lowest energy orbital. Now we move on to lithium. Lithium, we've got to move to the next highest energy orbital. Then beryllium, then boron, carbon, nitrogen, oxygen, fluorine, neon. And now again, we've got to move on up when we move to sodium. 1 up in the 3s, then magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon.